So hi everybody, this is Guillaume Reinisch. I'm going to make you a short presentation about the impact interface. So the impact interface is an interface to manage multiple C++ libraries and to interact with them in a consistent, intuitive and user-friendly way. So to begin with a very short overview, so here is the main window of the impact interface. On the left side you have everything related to the data structure. So here I just launched the application, so we have only one empty workspace. Here we have all the methods available for your objects. Here at the bottom of the screen you get the Doxygen documentation of the code presented to you contextually. That means that, for instance, if I click on one method here like getChild, we have displayed the documentation of the getChild method. Here on the right side there is a graphical panel in which will be included different widgets. We will see that a little bit later. And in the middle there is a scripting widget which is empty here, but you can create a new sheet here. And this is a Python scripting widget, so you have to code using Python, and if you do, for instance, print hello world as usually, and if you run it here you get the hello world printed. So what I would like to do here for this first kind of tutorial is to create a polymer and to parallelize this polymer. So first thing we have to do is to create actually a polymer. So we are looking into the new object menu and looking for something called MS Polymer here. So here in orange you can see the inheritance structure of the polymer class actually. So polymer is derived from microscopic phase, which is derived from physical interface, and basically everything here in impact is derived from the treemapper class. So you click on the polymer, and to create a new polymer you have to provide a variable name, so polymer for instance, and to select a parent object. Here we have no choice, so the workspace. Alright, so you have the polymer object created. You have different graphical widgets here on the right side, and everything is basically empty and not initialized because we didn't initialize actually the object, we just created it. So to see how to initialize the object, you can look at the different function methods listed here, and you see there is one load method, which is probably what we should call. Okay, this load a polymer model. It takes two arguments. The first one is a path passed to the XML mechanism. The second one is the ID of the phase in the XML mechanism. So we are going to call this method by clicking here. We need to insert a file name, so there is a shortcut here, insert file path. Alright, this is a phenolic.xml file, and the ID is phenolic. You can execute it, and now already you see that's way better, and everything gets initialized. So what do we have here? So you remember the polymer phase was derived from the microscopic phase, physical interface, and finally the treemapper. So here you have the same inheritance structure displayed here. So at the bottom you have the polymer widget, here the microscopic phase widget, alright, here the physical interface widget and the treemapper widget. So in the microscopic phase widget, what we can see is the different mole fractions of the spaces included in the phase and the net production rate of these spaces, expressed in entities per cubic meter per second. So I would like here to point something out, which is how the units are managed in impact. So basically every kind of object derived from a physical interface are associated to a units manager, which basically defines a unit system. That means that each time you are going to provide an input number to an object, the units used to interpret the value provided will be the units defined in a units manager, and same for the opposite way. When an object will return a value to you, you will have to use a units manager to interpret which units are used. Okay, so for instance, here if I'm changing, okay, I prefer kilocal for energy, and we are going to use mole for quantity. So everything gets updated here for the net production rate, and now the unit is mole per cubic meter per second. Okay, if we look at the kinetic mechanism of the polymer phase, okay, the activation energy are expressed in kilocal per mole. So just a short description of what is a polymer kinetic mechanism. So a polymer kinetic mechanism is composed by submechanism, here 4, 1, 2, 3, 4. Each submechanism transformed a subphase of the polymer into gas phase spaces. So for instance, the first mechanism transformed the virgin phase of the polymer into H2O. Okay, there is 3 Arrhenius parameters: the per-exponential factor, the beta parameter, and the activation energy. Obviously, you can change everything by clicking on the set button. Alright, what you can do also is to look at the data structure of the object created. So we see that the polymer is composed, okay, again by a kinetic mechanism, a parameters manager, phase, and a unit system. If we click on the kinetic mechanism, so we have much more information about the kinetics. So we have the creation, destruction, and net rates for the different spaces, and for each reactions, here you have the forward rate constant, reverse rate constant, and the forward, reverse, and net rate of progress. Okay, if you click and you open the phase object, you see there is a bunch of constituents, and there is a bunch of elements here: the oxygen, hydrogen, carbon, and nitrogen. If you click on one element, you have also a lot of information about these elements. So this information are coming from the Blue Obelix database, which is an online database on the web, but anyway. So this is useful actually to look at the data structure of your object, because the data structure displayed here is very, very closely related to the C++ data structure. So when you are working like this with Impact, actually you get used to the C++ architecture of the code. Anyway, so now we have initialized the polymer. We would like to pyrolyze this polymer. So we are going to create a pyrolyzer. Okay, this is in physical interface, derived from the reactor, and you have a pyrolyzer here. We are going to call it a pyrolyzer. I don't remember. Yes, and execute it. So you have the pyrolyzer here. When you don't know how to create your object, you can look at the description, define the pyrolyzer for polymer phase. You can see there is an example, and basically what we have to do here to first set the phase, so set the polymer phase. Alright, new object, method, and set phase. Alright, we are going to select the polymer we just created, and here. So what we can see here is, okay, the phase is a polymer pointer. Okay, a pointer means that it's not a new object, it's pointing at something else, and something else is this polymer we have created just before. So basically, this object and this object are exactly the same. This is the same object in the memory of the computer. So if you change something here, the same thing will be changed here. Okay, another thing we have to do to initialize the pyrolyzer is to set the temperature profile. Okay, you can set any kind of temperature profile using this method and using a scalar function object. So anything derived from scalar function. You can go here, so that means any object here. Okay, but we are going to use another method to set the temperature profile. We are going to use the set constant temperature profile. It's going to be a little bit faster. Okay, so method, pop-up method box, set constant temperature profile, and we are going to set temperature profile to 1500 Kelvin, for instance. Alright, and there is one last thing we would like to do is to increase the end of the simulation step here. simulation time, sorry, here to 1 second, for instance. Okay, so now you're done. You can call the run method, execute it, and now you're good. So the polymer has been pyrolyzed for 1 second at 1500 Kelvin. So there is one thing you can check here is the temperature profile. So this is the R from scalar function, so you get again this kind of widget. If you click here and plot, you see the temperature profile, so 1500 for 1 second. Well, it's not 1 second, it's 0.001 second. So we are going to reset the temperature profile because we change actually the end of the simulation time after having set the temperature profile. So we are going to do it again very quickly. Set constant temperature 1500 and execute it. Let's see if it's better. Okay, this is going to 1 second. This is consistent. And if we look at the polymer, of course, it's no more the virgin state, and basically everything except maybe the H2 at the end get pyrolyzed to some gas phase spaces here. So to finish this tutorial, what we would like to do now is to track actually the concentration of one species or multiple species during the pyrolyzing process. So to do so, there is one method here related to it, which is add tracker. Okay, add a tracker to the reactor, and at each simulation step, the value of the properties targeted by the tracker will be stored in a scalar function, basically a vector scalar function. So let's create a tracker. Mass fraction tracker we are going to use. We are going to call it ch4 because we are going to track the ch4 function, and in a workspace. Okay, now we need to use a set tracked object of the tracker. Alright, so set tracked object. So we want to select the ch4 constituent, execute here. And actually we are going to use another tracker, which is a ch4 condensed virtual species. So new object, there is a quick launch here, so there is a shortcut, ms tracker mass fraction, ch4 condensed, okay, in the workspace. Okay, this is not a big deal, it happens, and we are going to set the tracked object. So polymer phase and ch4 condensed, it's this constituent. Alright, so we're good here. So now in the pyrolyzer we need to call the add tracker method. Alright, we'll do it right now, and we add the first tracker, and same for the second. Okay, pyrolyzer, up. Execute. Okay, so now we have two trackers associated to the pyrolyzer. They are here. Okay, this is pointer to these trackers. So let's pyrolyze again the polymer. First thing, we want to restore the virgin state of the polymer. I mean, it's not mandatory, but this is what we want here. And then we have to run the pyrolyzer. Okay, run. Alright, great. So let's look at the ch4 tracker and the values here. So we see the values here, and we can plot it, and we get the ch4 mass fraction during the pyrolyzing process. Okay, we can do the same for ch4 condensed, but now to finish this tutorial, I would like to plot both of the ch4 and ch4 condensed mass fraction on the same plot. So I'm going to create a plotter, which is here. Okay. To include it in the workspace, again, plotter, we can see here there is add function method. This is the one we want to call, basically. So method, add function, we are going to select the values of the first tracker. Alright, plotter, add function, and we are going to select the second one, the values of the second one. Okay, so we have the plotter here. So there is no ID actually for the scalar function. So we are going to set the ID very quickly. So method pop-ups, Everything about ID, variable name, child is in the tree mapper structure. So set ID, ch4, gas, right, and same for the second one. Set ID, ch4, condensed. Okay, let's go to the plotter. Let's select a blue line for this one, a red line for this one, and we can plot it. And this is it. So we have the CH4 condensed species concentration in blue, the CH4 gas species in red, and we can have the evolution of the mass fraction during the pyrolyzing process. So one last thing, this time it's a really last thing. So we are going to save everything, save database, example 1, okay, save. We are going to replace the previous file. Okay, let's run impact again. Let's open a file, this one. Go to the plotter and plot. And well, that's great, because we have everything exactly in the same state. We left it just before quitting when we saved all our database. So that's it for the first tutorial. I hope that you did understand something here, and thank you.